Hello everyone, my name is Max, and I'm the team lead for the Gaffney Orthotics Computer Science Capstone team, and this presentation will cover our project, Ortho3D. I will be guiding you through most of this presentation, though you can look forward to hearing from each and every one of our team members as we get further along. To begin, what is our project? Our sponsor, Gaffney Orthotics, works in the orthotics industry, and wanted a free, easily accessible tool that could be used to digitize the process of making foot-ankle casts for patients. To this end, we developed Ortho3D, which is a web-based 3D modeling software aimed at allowing orthotics professionals the ability to fine-tune 3D models of patients' legs in order to later print a mold for a cast. Ortho3D is split primarily into two components: a front end written in JavaScript using the React.js library, and a backend written in C++ compiled to WebAssembly using Emscripten. Graphics are handled by OpenGL, which is a C++ API that utilizes hardware acceleration to render 3D graphics. With all that said, let's jump into the demo so I can show you what I'm talking about. Alright, welcome to the demo for the Gaffney Orthotics Capstone team. This is our software, Ortho3D, and I'm going to show you some of the cool things it can do. First of all, I'd like to draw attention to the UI. We've got this huge canvas. It's designed, to take up almost all the space so that that's the focus of the screen. Our our menu system is pretty minimalistic, and additionally, our menus float. So View, this controls our zoom and allows you to go to full screen. Edit, this is where you manipulate vertices and do other manipulations to the model. Select, this is where you select what parts of the model you want to manipulate. And camera controls, this is where you can input numeric commands for the camera. All exist on these floating menu items. They can be put anywhere on the canvas you want so that nothing important is ever covered up, and so that they also maintain their usability. You always have access to these features, but they also aren't in your way because you can put them where you need them. Furthermore, these are persistent. You can close them by clicking on these. They're on their respective buttons. But if you want them back, they will stay where you put them. So that's very handy. Alright, next, let's take a look at a file, at a model. Go ahead and upload this foot file, which is an STL of the ASCII format. And then I will show off the camera controls. Okay, so we're a little zoomed in to start with. So I'll open up my view menu, zoom out. Now we can pan around by holding the middle mouse button. If we want additional camera functionality, we can select the Move Camera button. And now with right click, we can control the facing of the camera. And with left click, we can move the camera in relation to the model. Next, let's cover vertex selection. We have three methods you can do that. We'll need to go under the select menu to bring those up. I'll bring it back here so I can see it. Now there's three modes. There's vertex, which allows you to select an individual. There is section, which allows you to select a group. And there is cross section, which allows you to select a slice of the model. We're going to skip vertex because we're limited on time, and we'll go straight to section. So by drawing a box, you can capture any vertices that are inside the box. This is great for manipulating a group as a whole, that might be protruding off of the foot or something like that. For cross-section, works a little differently. You instead get two lines on the model, and you can then select, you start with one line, and then you get a second line, and wherever you put that, it selects the vertices in between. Okay, cool. Now, next, I'm going to show off our undo and redo features. We'll get rid of these menus. And we will go to Edit, and we will go to Scale Model. We'll scale this model a few times. Let's start with 5%. Tiny foot. We'll do 50%. We'll do 150%. And let's go crazy, do 1500%. Bigfoot, not very useful. So let's go back. And we can now go all the way back to our original state, and likewise we can now go back the other direction as well. So it's very useful. Alright, and now for the final thing in the demo, I want to show off some actual translation and show off our file export. So, we'll go ahead and use the section mode for this demo, and we will go ahead and select, let's say, the top of this guy's foot. Right like that. That looks good. Now we can go ahead and look at this from a different angle, and yeah, that looks like a pretty good cut, so we'll move back. And now you see these three arrows that are on top of, that appear in the center of all the selected vertices. This is the primary way, the most usable and user-friendly way to adjust the vertices. If we open the edit menu, you can see that we have numeric ways to translate the vertices as well, but for this I'm going to show the UI version. This translate factor down here affects how much these arrows affect. If we select mode needs to be disabled, but now if we do this, you can see they move very slowly because of how low the translate factor is. We can go ahead and increase this a little bit. You can now see it's moving much quicker. We'll go ahead and move it back a little bit. So we've effectively, extended this guy's leg a little bit. Not a huge difference, but good enough for this purpose. Now, if you'll recall, this was an STL file, so just to show off translation between formats, I will go ahead and select OBJ, and now select Export File. And we get this file down here, and as you can see, I've done this a few times already today. So if I click on this, it'll open up in Windows 3D Viewer, and as you can see, here is his leg that has been extended just a little bit. So yeah, thank you very much for watching our demo. One of our primary goals when building Ortho3D was accessibility. Our sponsors wanted software that was freely and easily accessible to anyone, anywhere. That way, any orthopedic professional can take a scan of a patient, load it into our software, and edit it to suit their needs. To that end, we designed our software as entirely web-based. This means that users do not have to download or install anything to use Ortho3D. Because JavaScript is known as a predominantly slow language, and because 3D modeling is often a resource-intensive task, we decided to use C++ compiled to WebAssembly in order to try to maximize performance. Continuing the theme of accessibility, we also designed our software to be compatible with most common browsers, such as Safari, Chrome, and Microsoft Edge, and to support both the STL and OBJ file formats, which are the most commonly used file types for 3D models. Finally, because precision adjustments are necessary for Ortho3D's primary audience, most of our manipulations can be done using precise numeric inputs. As mentioned previously, our software is tailored towards the orthotics industry, and our intended user base is professionals from that field. We do not expect them to be computer experts, but we do expect them to have some familiarity with 3D modeling tools, and also to have hardware that meets our minimum specification. Furthermore, we expect our users to have a model to import into the software, as we do not support starting from scratch. The main features of Ortho3D are as follows. The software is entirely web-based. It includes import and export support for both OBJ and STL file types, including both ASCII and binary STL files. As far as manipulation, it supports selecting an individual vertex, a group of vertices, or a cross-section of the model. It also features the critical ability to both undo and redo changes made to the model. Next, you'll hear about all of these features in more detail from some of our team members.
Hi, my name is Stephanie Beagle, and I'm going to be telling you about our web-based software feature. An advantageous feature of our project is that the software is entirely web-based, and this allows our product to be freely accessible anywhere with internet access. Entities who might use our product in the orthotics industry don't need to worry about the overhead of installing a software product on every single device, and future developers can make changes to the software without requiring an update on the user's machine. A web-based software grants a lot of potential to both the future users and future developers of this product.
Hi everyone, my name is Philip, or Phil for short, and I will briefly go over Ortho3D's file support. In terms of 3D models, the most common file types are .objs and .stls. We decided as a group that it would be in the best interest to be able to support both. Thus, we implemented the functionality to be able to import and export said file types. Our implementation allows Ortho3D to be able to support both STL file types as well, ASCII and binary. Through various testing methods, we saw that other applications/softwares were able to load 3D models exported from our software. We also compared our model rendering with other applications/softwares such as 3D Viewer for accuracy, and the models matched when compared side by side. Thus, users can expect good compatibility with majority of other applications and tools and 3D model rendering.
Hello, my name is Carlos, and I will be talking about our main UI. The 3D workspace generated by Emscripten is displayed through a canvas element, which we have automatically sized to fit the web page as much as possible in order to minimize distractions. We've also designed the remaining UI elements built with React with this philosophy in mind. The main toolbar along the top allows users to access core functionality and display floating menus that they can also position around the web page to their convenience, allowing them easy access to these controls, as well as minimal distractions and maximizing workspace.
Hello, this is Corbin Stark, and I'll be talking to you about the features we developed for model manipulation. Because Ortho3D is intended for use in the orthopedic industry, precision control was a must when we implemented manipulation. To this end, we allow the user to select and manipulate a single vertex or a group of vertices as selected by a box or by a cross-section of the model. Once selected, we provide a user-friendly graphical way to manipulate the vertices, as well as a precise method via numeric inputs. This allows users to be as specific as necessary when making critical adjustments to the model, while maintaining usability in other cases.
Hi there, my name is Chris, and I will be speaking about the undo-redo feature in our project. So that's something we felt from the start that it would be highly desirable to have when supporting a creative workflow. Some examples I'll bring up are Word documents, Photoshop, video editing, and in our case, computer-aided design. All of these you want to be able to move backwards and forwards when making changes to the thing you happen to be working on. So in our application, it maintains the state change history of STL and OBJ files that are imported into the workspace, and tracks any changes on an undo stack, and anything undone on the redo stack. Thank you.
Hello, Max again. While my team members just covered Ortho3D's primary features, there are a couple others worth noting. One is our pre-modification overlay. In order to visualize what changes you made to your model so far, we implemented the ability to display a partially translucent 3D image of the original model on top of your modified model. Another feature we developed worth noting is the second method of vertex manipulation we implemented, twisting. Basically, upon selection of a group of points, or vertices, Ortho3D allows the user to rotate or twist the group around their calculated center point. This provides additional flexibility when manipulating the model. Were we to have more time to work on this project, there are several things we would have liked to implement. The first and most significant is the ability to delete part of the model by drawing a line over the model and clipping part of the model on one side of the line. This would allow us to easily remove parts of the model that are unwanted. Another feature that would be useful to have would be Boolean operations, specifically addition and subtraction, which is the ability to add or subtract material from one model based on the way it overlaps with another model. Finally, a third feature that would have been nice to implement would have been selecting part of the model by drawing a bounded shape on the surface, which would let us manipulate a very controlled and defined group of vertices. This next section of our presentation will talk about how we went about developing Ortho3D, starting with the architecture. As mentioned earlier, our front end is built using JavaScript and utilizes the React library for building the user interface. This allowed us to implement features such as our draggable over-canvas UI elements you saw in the demo. Our backend, by contrast, is written entirely in C++, which traditionally would not be easily compatible with our JavaScript-based front end. In order to circumvent this while maintaining the performance benefits of the language, we use the Emscripten compiler to translate the code into WebAssembly, which allows us to execute it in the web browser, keeping all computational load client-side. Now, Corbin Stark, one of our backend developers, will go into a deep dive discussing how the backend used raycasting and other techniques to make model selection and manipulation possible.
Hello, this is Corbin Stark. I'll be talking about what we did to implement various forms of vertex selection and manipulation. First, we implemented box selection. This is a simple tool that can be used to select vertices. The user can click and drag their mouse to create a square on the screen that will select all vertices within it. We implemented this first by doing a raycast into the screen for every pixel, and checking if that ray collided with any triangles on the geometry. But that turned out to be very slow, although it was functional. After some trial and error, we eventually made a faster selection tool by performing the operation backwards. That is to say, we did math to convert all the vertices of the geometry from 3D coordinates to 2D coordinates, and then did a simple check to see if the XY of the 2D position was within the bounds of the square. The second selection method we were able to implement in the time we had was cross-section selection. The user can turn on the cross-section mode using either a hotkey or a UI button. When in the cross-selection mode, the user hovers the mouse over the mesh and a red line should appear on the mesh. After selecting 2 of these lines, all vertices within the 2 lines will be selected. This was implemented using a single raycast at the position of the mouse. When we calculated the ray collision, we can get the exact collision point. We took the y-coordinate of the collision point and set that as the y position of the line. The line is really just a plane along the y-axis, so the x and z of it are infinite, and we only need to find the y component. Although we didn't do this in the time we had, it wouldn't be too hard to have an option to do cross-section selection along either of the other 2 axes. For vertex manipulation, we tried to stay close to how other software does theirs. Blender uses a UI that shows color-coded 3D arrows that you can drag to move the selected vertices along the axis the arrow is pointing in. We followed suit and implemented a similar arrow system. The arrows themselves are just simple 3D models we imported in and rendered with a solid color and no shading. They are placed to the average position of all selected vertices, so they'll be centered. When you mouse over them, which is determined by raycasting once again, they will change their color to be brighter, sort of like an indicator that's being moused over. When you click on them, the selected vertices position simply moves in that direction. It wasn't particularly hard to implement, it's just addition. For rotation, it was a little bit harder. We had to calculate the center of mass of all the selected vertices and then rotate around that center of mass. Scaling was also kind of similar. We had to calculate the center of mass, but this time we also calculated the direction vector pointing from the center to all the selected vertices one by one, and then move them in the direction away from center. All 3 of these operations, translation, rotation, and scaling, can also be used by inputting numbers into a UI element. This is for more precise movement, such as if you wanted to rotate a small portion of the mesh by exactly 25.32 degrees or something precise like that.
Our team was composed of 8 members, 7 software engineers, and a team lead. Given the nature of this project, we decided early on that it made sense to split our team in 2. One team to tackle the front end, and one to tackle the back end. Responsibilities were divided in the following way. The front-end team was responsible for everything that the user interacts with. This includes the user interface, as well as the underlying server that supports it. The back-end team is responsible for the core functionality of the software. They handled the rendering, display, selection, and manipulation of 3D models. Finally, as the team lead, it was my responsibility to handle communication with the sponsor, organize regular Agile-style team meetings, and manage the development and progress of both teams, doing my best to ensure that everyone was supported and making consistent progress towards our goals. From the start, we knew that the workload was not going to be balanced between the 2 teams. There's far more for the back end to accomplish than the front end. With this in mind, we set up the initial teams with the back end being larger, at 4 developers, and the front end being smaller, with 3. As we got further into the development cycle, we realized that this was not enough and settled on a final configuration of 5 software engineers on the front end, 5 software engineers on the back end, and 2 software engineers on the front end. Our front end team was composed of Carlos Sotelo, Stephanie Beagle, and for the first 2 sprints, Christopher Teeters. The back end team was composed of Corbin Stark, Forrest Pearson, Philip Chen, Jacob Odell, and for sprints 3 to 5, which corresponds to the last 6 weeks of development, Christopher Teeters. For our development process, we elected to use an agile-style system composed of 5 2-week sprints with stand-up style meetings 3 times a week. We decided on 2-week sprints and meetings 3 times a week because we felt it was a good balance considering the fact that we had other ongoing obligations in our lives and progress would likely not be substantial enough on a weekly basis to consider each one as a separate sprint. We used Discord for focused communication, which allowed individual teams to have focused discussions in their respective channels, while also supporting group programming via screen sharing, voice, and video calling. Finally, we used GitHub for development and issue tracking, as well as Trello for objective tracking. The following are some of the major steps we took during our project. First was actually selecting the project itself, choosing Gaffney Orthotics out of our other options. Next, we determined what objectives would be realistic goals and looked into technologies that we would want to utilize during our development. After that, we presented our project to our capstone advisor and got the sponsor to sign off on our software specification. Next, we divided into teams and began development. During development, some of our noteworthy milestones included getting vertex selection and manipulation working, implementing undo and redo functionality, and remodeling our UI to include floating elements and a full-screen canvas. From the outset, we knew that this was going to be a complex and difficult project, and did our best to account for it. The technologies we were using were fairly new, and there were very few examples of them being used in combination that we could utilize as a guide. Additionally, the projects we selected was fairly complicated in and of itself. We attempted to account for these difficulties by being conservative with our objectives and by scheduling 2 weeks of development time at the end of the term to act as a buffer period for unexpected slowdowns. Despite this, we still underestimated the difficulty of the project and ran into the following issues. The first notable issue we ran into was with our stack. Emscripten is quite new, and there are very few resources available for using it, especially in conjunction with a React front end. Because of this, it was challenging to get them to work together, and took a fair amount of time and effort to make it happen. Because of our buffer, we are able to compensate for this delay without issue. Next, Jacob and Forrest will talk to you about a couple of other issues we ran into during development.
Hi, I'm Jacob Odell, and I'll walk through the difficulties we had setting up our importing and exporting capabilities, as well as incorporating the Assimp library. Early on, we realized that Emscripten did not support dynamically linking Assimp's shared object files, so in order to use the library, we had to copy the entire source code into our project's working directory and compile it ourselves. This allowed us to use the Assimp library to import our models, but once the model had been manipulated in the 3D workspace, it was really difficult to repackage those changes in a way that the library's exporter could handle. So we ended up writing our own .obj and .stl exporters.
Hey there, my name is Forrest Pearson, and I'll briefly be discussing some of the challenges we encountered while progressing on some of the more complex features in the project. To start with, these features such as a line tool, cross-sectional manipulation, or twisting posed a unique challenge that required us to look outside at similar open source implementations. They also required for us to explore and determine how to make proper use of familiar and new algorithms, such as matrices multiplication or raycasting, to achieve the desired results for each tool. Beyond that, the hybrid nature of the project, with it making use of OpenGL, Emscripten, C++, JavaScript, and React, provided a unique challenge in which possible solutions had to be adapted for this environment, with odd conversions and performance demands being of particular concern.
Unfortunately, despite our best intentions and efforts, we were unable to complete all the goals we set out to accomplish at the onset of this project, and we learned some important lessons along the way. Firstly, open early communication with the customer is extremely important. Because we communicated early and often with our sponsor, they understood the situation and were ultimately happy with where we ended up. So was I. Had we not disclosed our difficulties ahead of time, this outcome could have been very different. Another lesson we learned was regarding development complexity. While we tried to plan ahead for the difficulties we encountered, we did not adequately compensate for the difficulty of working on a complex project on top of an unfamiliar technology stack. Were we to do this project again, I think there's a couple things we would change. First of all, I think we would be likely to be more conservative with what we put into the software specifications, given the amount of unknowns we had at the start of this project. Additionally, I think we would maybe choose to either use an unfamiliar stack or work on a complex project, but ideally not both simultaneously, as I think that's where a lot of our issues stemmed from. And now, I would like to share with you a message from our sponsor. Quote, "This is a challenging project for a capstone project. The team did their best to implement most of the promised goals and some stretch goals in a very limited period of time. Many of the features were done from scratch, which I was not expecting. The communication was smooth, we had regular meetings for updates and questions. Overall, I think they did a great job. Frank Zhao." And with that, this presentation is concluded. As a final note, on behalf of myself and the rest of the Gaffney Orthotics capstone team, I would like to extend our sincere thanks to our sponsor Frank, to Stephen, and to our capstone advisor Bruce. Thank you very much for making this a valuable and pleasant learning experience.